And this is my partner Javier Serrano. We will talk today about dual laterolog. This is the agenda that we will cover through this presentation. So we have some introduction, application, measurement principles, a specification of the tool, and calibrations, and to finish some LQC. So to start with the introduction, laterolog tools, we use it because we want to measure resistivity. And as you can see on Archie's equation, resistivity is one of the primary inputs that we want to know to calculate water saturation. Why we want to know water saturation? Because as you can see here in this picture, we have water and hydrocarbons. If we know the water saturation, we can identify how much hydrocarbons we have downhole. The basic principle behind the Laterolog tool is measuring the voltage between two electrodes. So as you can see on this picture, what we are doing is we have an ammeter and a voltmeter measuring the voltage between 2 points of the wire. So that's the basic idea. What we do is we know how much current we are forcing into the formation. We measure what is the voltage that we have down there, and by Ohm's law that we have right down here, we can calculate the resistance of the formation. Most tools measure resistance, and then they compute it with a K factor or geometrical factor that we use for the resistivity equation, which is driven by the area and the length of the formation being measured.
Okay, so when the drill is being, when the borehole is being drilled, we're gonna get this invasion model, right? We're gonna have a flush zone, the transition zone, and the uninvaded zone. So what is important here is that to describe the borehole environment, we need to have a resistivity measure at different depth of investigation. One here, and one here. Our tool, the dual Laterolog, measures deep resistivity, more likely here in the uninvaded zone, and the shallow resistivity here in the transition zone. Down here, we can show the resistivity profile that works better for this tool. It means that this tool works better in a salty mud system. So that means the RMS is going to be similar as the water resistivity of the formation. So as Fabian said, one of the main application of this tool is get resistivity in order to get water saturation, right? Also, from this tool, we can get a spontaneous potential using a variety. With this resistivity measurement and the measurement from RXO, from previous explanation, we can use a lateral tornado chart in order to compute RT and also have the invasion estimation. So water saturation calculation, as we said. So in the log, we can see if there is a permeable zone by looking at the curve, right? If they separate, there might be an invasion or not. Also, this tool works for correlation from well to well.
So the basic resistivity measurement. What they start with was this called spherical flow. What they did is that we put an electrode and we through a wire, we transmit current through a formation spherically. Why we say spherically? Because that electrode was spherical. So with this measurement, we were getting resistivity of the formation, but taking in account all the layers from the depth we were measuring in all the way up to the surface. Then they decided to put another electrode. What for? To make sure that we have a small measurement and less affected by all the layers. So right now we have A, which is the current emitted electrode, and we measure the difference voltage between A and M. As you can see here in the formula, we are using Ohm's law, but we are also taking into account the K factor, which again is driven by the area and the length of the formation being measured.
Before you can continue, we have a tool that works under that principle. Do you know which one is it? We saw in the previous slide.
Close.
Two only. Well, only one, yeah, from the previous slide. Macro, yeah, that's right. So what they did next was to add another voltage electrode, right? So now we're still having the same current emission and returning to surface phase, right? But now we're measuring the voltage just here in this portion. So from this we can get the measurement just for a portion of the formation. So it's better for understanding and for interpretation. So at the end we're going to have the same resistivity calculation driven by the K factor. That's the geometrical thing about that. And we're going to have the voltage difference between those electrodes and over the current that is being emitted. Okay. After that, what they did was to change the shape of the electrode in order to make it more likely for the borehole's shape. So as you can see here, this has a cylindrical shape. So it looks more like the borehole, right? By doing this, we make sure, or we try to make this equipotential shape cylindrical as well. So we can make sure that the current is being emitted perpendicular to these surfaces. And
Okay, so now we will enter into the focusing, which is our dual lat does. So there are two types of focusing, passive and active focusing. To start with, we'll start talking about the passive focusing, which is commonly known as LL3. Why 3? Because we have 3 electrodes. So what they did is that before we had a current emitting electrode, and they had 2 more electrodes to back up that current. So we have one bucking electrode, measure emitting electrode, and lower bucking electrode. So we are trying to push the same amount of current on the 3 of them to make sure that the current goes laterally and deep into the formation. Then active focusing came up. What they did is to add 2 more electrodes, these 2 right here, to measure the voltage between the current emitting electrode and the bucking electrodes. Why do that? Because, as Javier said, we want to make sure that we have equipotential surfaces. So with those electrodes, we make sure that the voltage there is 0. And if it's not 0, the tool itself will adjust the current emitting, the amount of current being emitted to make sure that that difference is 0. And we, again, make sure that the current goes laterally into a formation.
so once that they find out how to make the current go or flow laterally, right? Focus. They improve it. How? They added 2 more electrodes. These 2, right? So by changing the configuration of the electrode and the returning electrode, we can have 2 depth of investigation measurements. These are the Laterolog shallow and Laterolog deep. So how does this work? For the shallow measurement, the measuring current is emitted and is returning to the electrodes above and below, A2 and A2 prime. Also the bucking current. So we're going to be measuring mostly the part near to the tool, to the wellbore, right? At the same time, we are having another measuring. That's the deep Laterolog. So for the deep Laterolog, these 2 electrodes works as a bucking current too. So making sure that these bucking currents are forcing this measuring current going deep to the formation and returning to surface. So it's good because we have 2 measuring at the same time at different depths of investigation in order to describe the wellbore, right? And also for the tornado chart that we're going to explain later. Now, talking about the more specific of the tool, as you all know, we have 2 versions, compact and the standard. All compact tools have OD of 2 inches and a quarter, right? The total length of the tool is almost, with the MLE and the 2 guards, is almost 30 feet. this tool weighs 100 pounds, more or less. The maximum pressure that we can take this tool to is 12.5 kilo psi, and the max temperature is 125 Celsius degree. Something important to say is the vertical resolution for every dual lateral tool is 2 feet, and the depth of investigation for the deep measurement is going to be 50, and for the shallow measurement is going to be 15.
Okay, now on the standard side, standard guys should know that this tool weighs way more than our compact tool. So it weighs 400 pounds. Its OD is 358. It's rated up to 20 kilo psi, 177 degrees Celsius. And as Javier said, it has a vertical resolution of 2 feet. Depth of investigation is a little bit higher than the compact one. For the shallow, we'll go for 16 inches, and the deep, 60 inches. Okay, tool configuration. So this is the full configuration of a dual Laterolog. So what we have here, and I will explain each of the parts of this diagram. At the top, we have 2 bridles. Why we need bridles? To make sure that we isolate the tool from the cable armor. So they work as isolators, and we also measure SP and Groningen effect that we will explain later. MCG is our communications gamma. We use that tool to communicate the dual Laterolog to the surface system, and also to provide power to the Laterolog tool. Then below we have the MUG, which is the upper guard, or the electrode that we have been calling A2, which is just a bucking electrode. And then in the MLE we have the 2 guards, A1 and A1 prime, and the current emitting electrode. Below we need a lower guard on an A2 prime, which is a bucking electrode. And we can use there, instead of a MLG or lower guard, we can use a micro Laterolog, as we saw in the last presentation, to measure RXO and calculate RT from the tornado charts.
Okay, for the dual Laterolog tool, the standard tool, I'm not very familiar with this, but it's kind of the same, right? The only difference is that we're going to have a panel at surface, and that is larger as well. So at the top we're going to have an electronic cartridge. That's going to be our returning for the shallow and our bucking for the deep. We're going to have a sound section where we have the measuring electrode and the bucking currents as well. And down here we're going to have the cartridge for the MRT. That's the micro resistivity tool for standards. Also, we provide shallow and deep Laterolog as the compact tool. So I said that this measurement is done at the same time. That's not completely true for compact tool. This is done in a cycle. This is called the measurement cycle. The whole cycle lasts 280 milliseconds. So it's a switching cycle, right? Each kind of the switch lasts 40 milliseconds. The important thing here is that we made the measurement in 2 parts, right? First, the deep part. In the deep part, the bucking currents are forcing the measuring current to go and return it to surface fish, right? And after that, we get the measurement of the shallow depth. And in this part, we use the surface fish in order to do the SP measurement. So we repeat this cycle over and over again, but it's very fast, so it's more likely to simultaneously.
Okay, so opposite to a compact tool that switches a DC power supply to make sure that we have deep and shallow, in the standard tool we measure actually at the same time. So how they do that? They transmit the currents at different frequencies. The shallow will be transmitted at 280 Hz and the deep at 35 Hz. As we mentioned before, vertical resolution of the tool is 2 feet, and depth of investigation 16 inches for the deep, and 60 inches for the deep, and 16 for the shallow. Talking now about voltage reference and length of array. Our voltage reference is always the cable armor, and the length of the array is driven by the distance between the A0 or current emitting electrode to the cable armor. So why we need to do that? To know that, because we have some correction charts that are supported. We have two actually, short one which is 48 feet and the standard one which is 94 feet. So whenever we are in the field, we have to make sure that we have the right length and the right inputs in the software to avoid compromising the measurement. If we don't have these lengths properly set up, we will affecting the K factor and we will get erroneous measurements.
So talking about calibration, we have a base calibration that is performed monthly, right? So here we can see the basic setup for the calibration. We have a resistivity network, a resistor network, where we can set a resistor value, right? So we connect that network with clamps to each of one of the electrodes, right? So by software, what we do is a 2-point resistivity calibration. And before, this calibration was done in 3 steps. Right now, they improve it, and it's just 1 step. It's very easy and very automatically. Also, we have a base and field base and field check. This is done before and after survey. Here, what we are making sure is that the internal resistors of the tool are good. And also, we perform an SP calibration. We have an SP measurement, right? So by using a 10 millivolts battery, internal battery in the patch panel, we connect the SP electrode to the tool, and we measure and we make sure that the tool is working fine.
So as we do wireless measurements, we have some factors that affect our measurement. For the dual Laterolog, we have invasion, borehole size, borehole salinity, Groningen effect, casing effect, and side bed effects. One of the most important, I would say, is side bed effect. So we have 2 phenomena happen here: the squeeze and anti-squeeze. When will a squeeze happen? When we have a low resistivity bed, and above and below we have high resistivity beds. So what will happen is that the current will be even more pushed into the formation and more focused into that lower resistivity formation, and we will have an erroneously high deep resistivity measurement, and giving us also an erroneous invasion profile. On the other hand, the anti-squeeze, we have one high resistivity layer here, and above and below we have a low resistivity formation. So what will happen is that the current will take the easiest path, right? So it will go up and below and not in the formation that we are measuring. So we will be reading less resistivity than it actually is.
Another effect is the Groningen effect. This happens when we have a high resistivity bed on top of the tool, right? So we have said there is a current that is returning to a surface, right? So what happens is, because of this high resistivity bed, the current is gonna take the path of less resistance. That's gonna be the borehole. So in the log, what we're gonna have is the RT, our RT measurement, is gonna be higher than what it actually is, and we're gonna have a false invasion profile. So we cannot correct for that. We just measure it and make sure that we don't have that effect, and our measurement is good. So in order to correct for all these effects, we have different kind of charts. We have a thin bed chart correction, as you can see here, for correcting what Fabian said about squeeze and anti-squeeze effects. Also, we have a correction for borehole size. All resistivity tools have to be corrected for borehole size. And also, we have the invasion or tornado chart in order to estimate RT. One thing here is that we need at least 3 different readings: deep, shallow, and RTO, in order to compute invasion and RT from tornado.
So with this comparison between the dual lateral and the induction, what we want to show you is that lateral tools are usually run in high conductive modes or low resistivity modes and are used for high resistivity formation. The induction is total opposite to that, so we will be running the induction on high resistivity modes and low resistivity formation. So as a rule of thumb, RT, when it's greater than 200 ohms per meter, we'll use Laterolog, and when it's less than that, we'll use the induction tool. In this example log, we run a MDL, compact dual lateral log, in a 12.25 inches hole in Colombia, the Holy Land. So what you can see here is that we have two zones, two gamma ray showing clean zones. So in the bottom part, what you can see there is that all the curves are close to each other. So we can determine that is our wet zone. On the upper part, we can say that it's a hydrocarbon zone because we have a higher resistivity ring and the separation of the curves is much higher. Of course, we will need some other data to assure that we have wet zone and hydrocarbon zones, but for this example, this is what we are trying to show.
So, for conclusions, we can say that resistivity is our main, one of the main inputs in the Archie's equation in order to get water saturation, and at the end to get the oil saturation, that what is important for us.
Most tools measure resistance and they compute resistivity using a K factor or geometrical factor driven by the area and the length of the formation being measured.
Lateral devices are tools that force or focus the current into the formation.
With dual lateral tools, as Javier said before, we get shallow and deep measurements. To be able to calculate RT, we will need an extra measurement, which is from the MMR, and we will make sure RXO.
This tool works better in low resistivity modes and high resistivity formation, and also has a very good vertical resolution, and it has a good, better definition. Thank you. Any question?
How can you identify on a log a squeeze effect or an anti-squeeze effect?
A squeeze effect and anti-squeeze.
Do you want to explain or? You will need more tools, right? For example, if you have a micro Laterolog, which has a a greater vertical resolution, so we'll read the small thin beds, we can identify that easily. Just by looking at the lateral tool, you cannot tell.